So we need to use numbers in math from time to time. So let's look at numbers, different sets of numbers, and what kinds of numbers are in those sets. So the natural numbers are probably the simplest of numbers. Like when you were a little child, these are the numbers that you learned. Right? Basically counting numbers. You have 0 of something, 1, 2, 3, 4, and on up the way it goes. Nothing in between, just 0 to 1 to 2 to 3 to 4. Whole numbers. Integers, now you'll notice the integer box is this yellow box, and it has inside of it the natural numbers, or the whole numbers box. So those whole numbers, they are integers. They're inside the integers, but there are some integers that aren't whole numbers. And they're mostly these ones, negatives. -1, -2, -3, -4. Okay? Still nothing between them, no fractions or decimals there, just complete numbers, but negative. Then the rational numbers, all of these numbers are rational numbers, but then rational numbers that aren't integers or whole numbers, something like 3/4, 1/2, 2/3, -5/6. All these guys are examples of rational numbers. One integer over another integer. Those are rational numbers. We can write decimals that are also rational numbers. 0.5 is a rational number, it's a decimal, but it can be represented as 1/2. It's a rational number. 2/3 is 0.6666666 forever. Okay, that line over 6 means 6 repeats itself for eternity. That can be written as 2/3. Okay, even though that decimal goes on forever, it can be represented as one integer divided by another integer. So it's a rational number as well. Any decimal that ends, it doesn't go on forever, it can be written as a rational number. For example, like 0.97635. We write that as a rational number, as one number divided by another. Answer is yeah. So how would we do that? How would we write that as a fraction? How would you read that number? Or you got something, Nathan?
No, never mind. Sorry.
Something, you got something. It's more than nothing.
No.
What were you going to say?
I don't know. It's gone. Pressure's on. It's gone.
Okay. How would you read this number? Aside from saying 0.976 and so on. How would you read the number? How would you read a number like this? How do you read that number? Ethan?
39,765.
You said 100 already. 765, right? So 39,765. And how did you decide how did you know you were going to start saying 37,000 rather than 3,000 or million?
I don't know, common sense.
Common sense. Can someone put it into words? No. Names, lists. Somebody can explain it. Sam, do you have your hand up?
After every 3 numbers, there's a comma.
After every 3 numbers, there's a comma. Okay, one set of 3, right? Your first comma is 1,000. And how many thousand? 39,000. So it's just place value. You figure out what place this is in, and you know how to start reading this number. Same idea here. You got to figure out what place this is in, so that you know where you are. So what place is that 5 in?
100,000.
Where?
100,000.
100,000s?
I don't know.
Let's see. What place is this? Tenths. This one? Hundredths?
thousands, 10,000,
What is it? Thousands?
10,000.
10,000s? 100,000s?
1 million.
Millions. Okay. Where's the? So there's a tenths place. Where's the oneths place?
There is none.
No, it's right there.
Yeah.
That's the oneths place. That's where the units always go. Okay, so how could, knowing that that's in the millionths place, how many millions are we looking at? Okay, that's 5 millionths. Or we could say this many millionths. How many millionths is that? Can you read it? Nathan?
976,325
Yeah.
millions.
Exactly. Sorry, I cut you off there. 976,325 millionths. Okay, there it is. We wrote it as a fraction. Any decimal that terminates, that ends, you can write as a fraction, just like that. You figure out what place you're in, and there you go. That's how many of those you have. Even any decimal that goes on forever, but has a repeating pattern. So if this went on 167 forever, we could write that as a fraction. It takes a little longer, and we won't bother with you, but trust me that you can do it. So any number that goes on forever, any decimal that goes on forever but repeats, we can write as a rational number. But there are numbers that you cannot. There are decimals that don't end and don't have a pattern. Anybody think of one? You know one? Oh, it's your raising your hand. The pretty famous, what was that? You said. I heard it. What is it? Just steal it. Pi! Yeah, very good. Very, very good. You are good. Pi is an irrational number. It is 3.14159. That's all I know. And it just goes on forever. Doesn't have any distinguishable pattern, not that we know of anyway. And it just goes on forever and ever and ever. It's irrational. Square root of 2 is irrational. What about the square root of 4? Is that irrational?
No.
What is the square root of 4?
2.
2. So what kind of a number is the square root of 4?
Rational.
It's rational. Is it an integer?
No.
Yes.
Yes. Maybe.
Square root of 4 is 2. Is that an
Yes.
integer?
Yeah.
Could be.
Yeah.
Yes.
Right? Is it a whole number?
Yeah.
Yeah, it goes into even this little subset right here. There it is, 2. The square root of 4 is rational. But the square root of 3 or the square root of 7 or anything that doesn't have a perfect square root, that's irrational. Okay? So there's also this set over here called the imaginary numbers, and we won't worry about that for quite a while. So I can tell you the basis of the real numbers, really at the heart of all numbers, is the number 1. Right? And then adding 1 to itself a bunch of times, subtracting 1 from itself a bunch of times, we start to build the number system. The unit in the imaginary system is not 1, it's the square root of -1. We give it the name I, because it's faster to write I than the square root of -1 all the time. And we'll worry about that at a later time. I have an answer for that.
Hello? Sure.
Allie? You want your Go to the office. Okay. So, yeah, that's the whole thing that we'll get into later, just not right now. So we're going to be dealing with, for the near future, the rational numbers, which are real, the subset of the real numbers. Okay. And that's what we're going to be concentrating on. So we're going to look at how to combine them, the properties that they have. And first, we'll do, there was some trouble with the test, just like with number lines, so we'll talk about number lines real quick. If I tell you to graph -2.5 and -1.5, I saw quite a bit of just this, like something right there and something right there. Right. I need to be able to tell what these numbers are without being told what they are to start with. Can I tell what these numbers are just based on the number line?
No.
No. Gotta have some information,
You
yeah.
need a 0.
A 0, right? So I need a 0 like right there.
No, that's not
No,
even right,
in
like
the
right in
middle.
the center, on the center line.
That's not true.
I'm wrong. Yeah.
Yeah, you are.
0. Now, we're used to putting 0 in the middle. That makes sense. It's kind of the center of all of the numbers. You got your positive numbers over here, and you got your negative numbers over there. But you don't even have to have 0, really. You just need some frame of reference. Okay? So this needs to be 1. This needs to be 2. I prefer that you put 0 if it's on the scale, but if I ask you to graph negative 137 and negative 150, I wouldn't expect you to start way over here at 0, go all the way over here with 137 and 150. Right? So on the number line, I guess it depends on what we want to do. But I guess that's just not something I would ask you to do. To get that to be 0, we would have to come way over here to be negative 137, and then we have to figure out the scale of it and figure out where 150 would be. I don't know. This is all kind of a bad rabbit trail. My point is that when you do 0, 0 can be here, or it could be over here. It's just a frame of reference. It's not required to be in the middle. So between negative 2.5 and negative 1.5, which is larger?
1.5.
Negative 1.5 just jumped out there. Negative 1.5 is larger. How do we know? What tells us it's larger? Well, right down. Nathan?
Because it's closer to 0.
Closer to 0. So 1 is larger than 2.
No.
It's closer to 0.
On the negative side, that 1.5 is closer to 0.
Uh-huh.
It makes it a bigger number because forget it. We're done.
What's a universal rule that will always work? Jared?
What's farther to the right?
Okay, farther to the right. No matter if you're on the left of 0, on the right of 0, if you're farther to the right, you are larger. Hunter, did you have something?
Yeah, when we, like, the dots that you have are representing the numbers, do you want us to write the numbers, like, negative 2.5 on top of the dot? Or
if I'm having you do 2 numbers, then yeah, you want to
Okay.
label it just so that I'm sure that you know this is a negative 2.5.
Yeah.
Right. Yeah. Now, number lines like this, we've done since, I don't know how long ago we did number lines. They started a long, long time ago. So they're fairly basic. They are going to, like the skills that we know about number lines are going to come in useful when we do graphing, right? You've graphed things before, right? Maybe not a ton, but they have, it's basically number lines, right? Here's a number line. And for convenience sake, we do put 0 right there, and we mark off some tick marks there. So this number line is horizontal, so we call that one x. Okay. Then the thing is, these graphs are going to relate one variable to another. You do something, you put something into an equation, and it pumps out this other number. You got input and you got output, and we could graph the input, but then we'd have nowhere to put the output. So that's why we have a second number line, and we just put it that way. We call that one the y-axis. Okay. Now we're not going to get into this today.
Please excuse the interruption. Please release high school football players at this time. Please release high school football players.
Bad
Thank you.
distractions. Yep. It'll be on the website and text message as well.
All right.
Thank you.
Can I take a picture of that?
Sign up for text message?
Yeah.
It'll come out that way.
Adios, amigos.
Alright.
Pancake.
It'll be sent out at 3:15.
There.
Huh?
Probably gonna be a little bit.
Alright, so those were some issues that some had with number lines, labeling, and give me some idea of where we are. 0 is a really good indication of, it tells me you know where the negative numbers are. They're on the left side. It tells me that you know how big these numbers should be, how big these tick marks should be. I could have graphed this, and some people did. Could have graphed it a little differently. Could put 0 there, and there's 2 tick marks. That's 1, and that's 2. So I get to use the tick marks for 1.5 and 2.5. You could label these 1.5, negative 1.5, and negative 2.5. All depends on how you choose to do it. It's just a matter of choice of scale. What's the opposite of 6?
Negative 6.
Okay. What's the opposite of negative 6?
6.
It's 6. Very good. Okay. So if negative 6 is the opposite of 6, then they're opposites of each other. So 6 would also be the opposite of negative 6. All right. Now, what do those mean?
I have no idea.
Yes, Emma.
Absolute term.
Absolute
Value.
value. Absolute value. Okay. What's the absolute value of negative 6?
6.
You're just gonna have to shout it out, I guess. Just excited. Absolute value is 6. What's the absolute value of 6?
6.
6. Okay, so can we define absolute value some way?
Absolute value is the
Just
whole number
information.
without. I don't know.
Okay.
It's something.
We could call it that. The number, but not negative. Always positive, we could say. All right. What's that?
Why bother putting a negative in there?
Well, yeah, there's not really any sense of just writing it that way. Like if I wanted to write you a letter and tell you about the number 6, I wouldn't write it this way. I'd write it just in 6. But absolute value is we'll call it an operator. Okay, and sometimes it's useful to take the absolute value of a number, but you're not always, in the context of whatever problem you're talking about, you're not always going to wind up with a positive number. So you kind of want to have like, it's more useful if you have like the absolute value of x, or more like the absolute value of maybe 75 minus x. So that even if x winds up being bigger than 75, all I want to know is like how big is the distance away, that x is from 75. That makes sense? 75 minus 50, that's 25. 75 minus 100 is negative 25, but I just want to know how big is that gap. It's 25. Right? Makes sense? And what you would do with that is like use it in a formula or something like that that calculates whatever you want. Okay? Like, I don't know, on the spot. Let me think about it. I might have to tell you next class. But it's we just plug numbers in there, and you tell me what the absolute value is, so that you can display that you know what the absolute value means. So if you see it somewhere else, you know what it means. Okay. So, what is this worth? And what's this worth?
7.
I have no
No,
idea.
negative 7.
Negative 7. This is 7. That doesn't change. But we just made whatever comes out of this thing negative. So it's a negative 7. What about this?
Remembering that.
What's that worth?
7.
7. Okay. So there's a question similar to that with 7s, and which ones are 7s and which ones are negative 7s that maybe half did correctly. So let me go over that. Okay, let's talk about putting numbers in order, particularly numbers that are, you're comparing decimals and fractions in the same place. So, 16, negative 1.66, 5/3, and negative 1.6. One thing that I noticed in the test, a lot of answers, you start out with a fraction and then you wind up giving me an answer in a decimal. Okay? I didn't ask you to change it to a decimal, so you should assume that you leave it as a fraction. There's very few instances where you should, if you were given a fraction, answer with a decimal, or vice versa. If I ask you a question about a fraction, I want to know the answer about that fraction. Especially, here's the big problem, 1/6, or let's do 1/3. If you just take 1/3 and you say, that's 0.33, and you tell me that it's equal to 0.33, you'll be wrong. It's not equal to 0.33, it's equal to an infinite number of 3's after a decimal. So this is not equal to that. They're not equal, they're approximately the same. And especially if you use this to calculate something else. You multiply 0.33 by something instead of 1/3, it's not the same thing. It'll be close-ish, but it won't be the same. So if it's not necessary, if it's not necessary to change it to a decimal, leave it as a fraction. And it's not necessary to change it to a decimal. Okay, so now we need to put these in order from least to greatest. And which of these would be the very least out of all of them? Nathan?
Negative 1.66.
Okay, why is that?
It's the least.
Anybody with a better answer? Even Nathan. Yeah, Jared.
Negative 1.6.
Right.
No, I want to know why this is the smallest. Yeah.
Because it's hundredths
Huh?
more negative than 1.6.
Yeah, I like that. I like it. It's 6/100ths more negative than negative 1.6. You got 1.6 and 1.66. At least the size of it, the magnitude of it, is larger, right? But it's negative, so it's further to the left. So next is negative 1.6. And what would be next? 5/3? Or is it 16?
Thirds would just be
1 over 2/3?
1 whole.
1 whole and 2/3. Yeah, 5/3 is just 1 and 2/3, and 16 is a lot bigger than that. So let's leave it as 5/3. 16. We're going to do one where the fractions are a little closer, a little harder to compare, but something about 5/3. Should you write it as 5/3 or 1 and 2/3?
5/3.
Huh?
5/3.
5/3?
Wait, no. Wouldn't you have to make it a, never mind.
What can we say about these two numbers?
They're equal.
They're equal, okay. So is it wrong to write it this way, like your answer is this? No, it's the same as that.
Yeah, shouldn't you leave it as this answer in the problem?
Yeah, and if it started that way, leave it that way, okay? If you want to think about it as 1 and 2/3 so you can compare it to 16, that makes sense, but leave it as 5/3, that's what it started as. In elementary, I imagine you were told to write it this way. What's this called when you write it this way?
Mixed number.
Proper fraction, mixed number, okay? This is what's called a proper fraction. This is what's called what?
Improper fraction.
Improper. I don't really like that. It makes it sound like it's, I don't know, it's yeah, bad, improper. It's not proper, but there's nothing improper in mathematics about using 5/3. If I want to add fractions, or multiply fractions, or divide fractions, I need them always to look like this. One integer divided by another integer. If I'm looking at this, it becomes a lot more complicated to add 1 2/3 to 3 4/5. That only do, as we all know, have to find a common denominator. I then have to do what? If I want to add these together, what do I have to do with them? Yeah?
Take the 1 and the 3 and multiply those, and then add 2.
Oh, here?
Oh, yeah. Are you talking about the other one?
Either one, this one. So you multiply the 3 by 1 and add 2. You multiply 5 by 3 and add 4. And that's turning it into improper fraction. What do you do before you do any calculation with fractions? You always make them improper. So I'm not sure who decided they were improper because they are more functional and useful in mathematics. The thing that makes more sense is if you wanted to tell me how many gallons, whatever you wound up with, 1 2/3 or 3 4/5 is more, I can conceptualize that a little more than 5/3. What's that?
I have a question,
Yeah.
it's kind of off topic. What does a don't be a D3X mean over a DT?
You have to take calculus to understand that. Even my calculus students don't. It's one of the rewards that I offer you to take higher level math. You
I have a
understand that,
question.
Joe? Yeah.
Could you like look it up online and get the same answer?
Yeah. How rewarding.
You could?
Okay.
It's like the same as earning it, Toby.
Yeah. I'm so good at
I guess you could. I don't know. You could find the words. I don't know if you'll understand what the words are saying. There's a lot of calculus words that well, at least a few, that it takes to fully appreciate what that says. Let's try. Can you see that? It's a bit of a struggle to read. 6, -1. So let's start at the least. What is the least? Which of these numbers is the least? -1. So it's between -1, -0.6, and -2/3. Why isn't it -2/3 or -0.6?
Is that negative 11 or?
It'd be
That's
negative
it's a
2/3.
comma.
Oh, okay. I
I
thought.
think it'd be negative 2/3.
You think that one is furthest to the left?
Oh, never mind now.
Furthest to the left is
No.
1. Why? Why is -1 further to the left than -0.6 or -2/3? It's a whole number. 2/3 is less than and less than 1.6 is less than 1. -1 is furthest to the left. And what's next? -2/3 or -0.6? I know it's hot. -0.6 is further to the left than -2/3.
Yeah.
Why are you sure about that?
I don't think that.
Okay, so there's one option. We can put it in a decimal. If you were to take out your calculator and do 2/3, you're gonna get an infinite string of 6s. 0.66666 forever.
That's so cool. Like a little
Okay? So what's furthest to the left then?
Negative 2/3.
Because we're thinking to ourselves, this is -0.6666 forever. Now that's definitely further to the left than just -0.6, so -2/3, -0.6, and then there's not a whole lot of reason in debating that because it's the only positive number on that list. So you need to make them comparable. You could just use your calculator and put it into a decimal. You could make the decimals into fractions. What fraction would 0.6 be? -6 would be -6/10. Can I compare 6/10 and 2/3? Yeah, no. Which is bigger? You just from off the top of your head, which is bigger?
6/10.
2/3.
2/3, 6/10. Why? Because what? Because we already know? We've already done the work another way, or not?
She thinks so.
I said 2/3 is closer to like one full, like
Oh, and it's 2/3 is closer to a whole than 6/10? How do you know? Is that a feeling you get? Yeah?
If you take do that thing where you make them equal, that one comes out to be 18/30ths, that one comes out to be 20/30ths. So,
What did he just do?
I don't know, you times 3 by 10 and 2 by 10, and you times 10 by 3, 6 by 3 to get them to be equal fractions. So you can just leave the choice.
They're not equal fractions would be fractions that are
No,
the
like
same.
equal on the bottom. What's the
Right?
bottom one called?
So what's that called?
I don't know.
Common denominator.
Common denominator.
Common denominator, you found it.
Yeah.
Okay, so if we take negative 2/3 and multiply this by 10 and this by 10, we get negative 20/30ths, right? And then this, you multiply this by 3 and this by 3, and this is going to be negative 18/30ths. You're close. We already knew that, right? 0.6 and 0.6 repeating. They're very close. This is only 2/30ths more to the left. So there's another way you can make them both into fractions with common denominators and see which, how they fall in line then.
I have a question.
Yeah?
Can we learn how to do fraction stuff?
The common denominator?
Like, yeah, I'll do stuff with fractions. We can do that later.
Today we'll be adding fractions, multiplying and dividing. Okay. From what I gather from the tests, most people understand that there are positive numbers, there are negative numbers, that positive numbers are to the right and negative numbers are to the left. But when I asked you to add them together, there seemed to be quite a bit of, I think maybe rushing through and not paying attention to the signs of the numbers or something like that. So if we have negative 10 plus 2, okay, where is negative 10 on the number line? Where is that? That way, it's 10 that way. And what does it mean to add 2?
It gets closer to the right.
Go that way too. Okay, so where would that put you in the end?
negative 8.
Negative 8. It got some negative 12s. Okay, what might that person have been thinking?
That the 2 was negative.
Maybe too quickly thought that the number 2 is negative. Maybe thought.
They probably thought it was like 10 plus 2 is 12, but negative and make 2.
Could have done that. Maybe just added the 10 and the 2 and gave the negative. Maybe thought we're moving in the negative direction and let's go 2 more that way. We're already headed that direction. I'm not sure exactly what, there could be several reasons why we would do that. Because it's, I can't tell you what the person who got it right was thinking either. There's several different ways to think of the right answer. So, I don't know. But I think whatever it is, it probably has a lot to do with maybe rushing through, not paying close attention. So, and I make mistakes like that. If I'm going too fast, I might come up with negative 12 on that. If it's a smaller part of a larger problem I'm trying to solve, I just have to be careful, pay close attention to everything that I'm doing. So that's really I can't really fix what might be wrong conceptually, because I don't think there's anything wrong conceptually. I think everybody gets positive and negative numbers. Just be careful, be a little slower. Okay, so we talked about these kinds of numbers. We talked about we're using the real numbers, and the real numbers have properties. They have properties. I'm just gonna erase this stuff. They have properties over. We say the properties of real numbers over addition. And then we can do the same thing, properties. I'm gonna just do that. Properties of real numbers over multiplication. We have commutativity. Okay, for real numbers A and B, if we say that A and B are real numbers, commutativity of A, B are real numbers, then A plus B is equal to, what do you think I'll write on the other side of this? Well, for any two numbers that we're going to add together, any real numbers we're going to add together, A plus B is the same as B plus A. If I were to say C, I wouldn't know what C was. All I know is that I'm adding A and B, and to bring C into it on the other side of the equation, kind of be to say that there's this other number C that's just hanging out there. What we know is that we can flip the order of an addition problem. Okay? That's commutativity. We have associativity. So if we throw in a C now, if we say A plus B plus C, doing those two first, we could say the same. It would be the same thing to add B and C first, and then add A. So this is drawing to our attention that you can't add three numbers together. Okay?
What's that? The second from last word, right?
This?
In front of addition. Yeah.
This? Over.
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 Yeah, that looked like or.
Try and write slower. So we can't add three numbers together. That's what I had said. What does that mean? If I say that we can't add three numbers, and I'm correct, and I am, then what do I mean by that?
You have to add two and then
Right. The operators that we have for real numbers only work on two numbers at a time. There is no multiplication facts for three numbers. They exist, but you just have to find them by multiplying two numbers together and then getting the result and multiplying it by the third number. Okay. So we have to draw our attention to two numbers, and whether we do these two first and then make this the third that we bring in, or we do these two first and make this the third one, it doesn't make a difference. They're the same thing. For multiplication, it's similar. Multiplication has commutativity and associativity as well. Commutativity for multiplication says A times B equals B times A, and A times B times C, where we group A and B, is the same as if we did A times B times C and group B and C first. Now these aren't something that I'm going to expect you to test on. I'm not going to punish you to take points off your grade because you don't remember which is which. When I use it, as you ask me a question, and it is guaranteed to happen at some point that you'll ask me, can we do this? Could we do this instead? Could I add those numbers first? Because I'll do it one way and you'll do it another way and you'll get the same answer, but we want to make sure that you did it correctly. But if you remember the associativity and commutativity, I'll say, well, associativity, multiplication is associative, and so yes, you can do it your way while I do it my way, and we'll both get the same answer. Okay. So, to help you remember which is which, let's look at the words. Commutativity. What's the root word of commutativity? Commute. What does it mean to commute? Huh?
To go places.
To go places. Yeah, if I commute, usually we're talking about to work. I commute to work, I drive to work, I travel from one place to another. So commute, why might that be an appropriate word for this property? What are the numbers doing? They're moving. They're physically changing where they are in the problem. A is not first anymore, it is coming after B. So they can move and change positions, they can commute. What's the root word of associativity? Associate. What's it mean to associate? If people associate, what does that mean they're doing? What do you think of them doing? Huh?
Work together.
Working together, how about that? Okay? If we look here, A and B working together. Okay? And after they get together, C gets in on it. And there's a result. You come over here, B and C are working together, and then A comes into the picture. But either way, it's the same thing. So the difference between commutativity and associativity, I remember mainly commute means move. Commutativity is where they change position. They actually move, change the order. 3 times 5 instead of 5 times 3. But it's the same answer. So let's do this. Let's just look at the exercises from 2.2. And look at number 28. 2.2, number 28, that's page 77. Page 77. Number, I forget what I said. 28, number 28. So it's saying what property is being displayed in number 28? Commutativity of addition. Right? We kind of qualify them. There's addition and there's multiplication. So commutativity of addition. 9 plus negative 1 is the same as negative 1 plus 9. Now, maybe this could confuse you, maybe it wouldn't. But so let's say 9 minus 1. Is it the same as 1 minus 9?
No.
Is subtraction commutative? No, subtraction is not commutative. But what are we really doing when we subtract 1? Wait, 1, are we adding? What are we adding? What are we adding to 9? Negative 1. You're adding a negative 1 when you subtract it. Is addition commutative? Yeah, it is. Right there. So what we have to realize is that subtraction is not commutative. We're not actually really doing subtraction. We're doing addition of a negative number. So negative 1 plus 9 is the same as 9 plus negative 1. So it's kind of rare I would see an algebra 2 class, but sometimes just switch and do the subtraction in the opposite order. And you don't want to do that because subtraction is not commutative. We're adding and subtracting, multiplying and dividing real numbers. Part of those are the rational numbers, and so we'll look at some rational numbers. If you're to add 3/5 and 2/3, let me just ask it this way. If I were to add these together, and if I weren't slowing down and thinking about it too hard, I might say that I have 5 of something. What I even say that was 5 what? Maybe, okay? Maybe that's like a common mistake that happens. People do that. They add the numerators and the denominators, okay? But you can't do that, right? Yes?
Do you need common denominators?
You need common denominators. Okay, so I want to not worry so much right at this moment if you know how to find common denominators, but why do you find common denominators? What's that? If you had been taught all your life to add these together to get 5/8, nobody ever challenged you on that, that's probably what you would be doing. Someone told you to do it. You would trust that your teacher was telling you the correct thing to do. Can we explain beyond that, beyond this is what I was taught and I know I'm supposed to, why can you not add those together like that?
That's just not how we do it.
What's that?
We just don't do it like that.
Okay, we need a, a stronger reason. There is a reason that's wrong. What does it mean? What is 3/5? What is 3/5? 3 out of 5? Meaning what? 5 being what?
The whole.
The whole. 5 is the number of pieces of the whole. So if I can draw fifths, then 3/5 would be that many. And 2/3 similarly would be 2 out of 3. 3 parts being how much you need to make up the whole. Let's say that you still maybe thought it was 5/8 and you didn't want to say so. If 3/5 plus 2/3 was 5/8, then this much plus this much would have to be, drawing 8s now, let's cut it to 8 pieces. This would be 5, so 4, 5.
That's less.
That is, yeah, it's less than, well, at least if I drew it very well, looks like it's less than either one of these. That doesn't seem right. So it can't be. We definitely at least have a convincing counterexample. It can't, the result of this cannot be 5/8. Because there's 5/8, that doesn't look right at all. Even if my drawing was bad and not to scale, it's still clear that this would come out to be more than a whole. Or at least it looks like it would come close to more than a whole. And that's less than a whole. So definitely is not the way to go. But still, why can't we add them together without getting a common denominator? What does it mean to get a common denominator? If I were to add these together and say that they were 5, what could I, 5 what? Why can't I finish that sentence? I have 5.
You don't know what it is.
You don't know what it is. Is this the same thing as this thing? It's the same? Is it the same size? Is that piece the same size as that piece? That's essentially it. You don't have the same kinds of things. If you had 3 oranges and 2 later bananas, just drawing messed up apples. I'm sorry about that. Apples are red, so I guess they could have been green. But if we had 2 apples and 3 oranges and I tried to say I have 5, I add them together, 3 plus 2 is 5. 5 what?
Fruit.
Okay, well, it's 5 fruit, but I can't just say I have 5 fractions, right? That's not going to work out too well. And that's kind of the same thing. They are the same thing. Those are fractions. These are both fruits. But other than that, I can't make these two things the same. But I can do it over here, because what these fractions are, as we said, is how many pieces make up the whole. We could change that. If we can use 5 pieces to make up this whole, we could divide each piece into equal pieces, like 2 pieces, and then we could say we're talking about tenths. Right? 10 pieces make up the whole. We could divide each of them into 3 pieces, and now 15 pieces makes up the whole. 4 each would be 20, and we could go on any multiple of 5. Could be what we split the whole into. Same with 3. We could do it. We could cut these into 2 each. We could have a whole that's cut into 6 pieces. We could go with 9 by cutting them into 3 each, and so on and so on. So we're going to divide this whole into the same amount of pieces as this whole so that they both have the same amount of pieces making up the whole, and we can compare the two together. So how many pieces are we going to want this?
15.
15, because we can also divide this into 15 pieces.
Yeah.
Okay? So how many times more than 5, right? This is 1, 2, 3, 4, 5. How many times more than 5 is 15? What's that? 3 times bigger. So we need to multiply by 3. Multiply by 3. Multiply this by 3, obviously, because we're also going to multiply these 3 pieces. Over here, by 5. We need to divide these into 5 pieces, so it's going to be 5 times more of those pieces. So we multiply the numerator and denominator by the same thing. The reason why we find common denominator is the denominator represents how many pieces make up the whole. And if a different amount of pieces makes up the whole, then it's hard to compare them and add them together, see which one is bigger. Like, until they're common denominators, we can't have them interact really. So we get 9 fifteenths and 10 fifteenths. I'm going to add them together. We get 19 fifteenths. So I said earlier it looked like these two would make more than one whole, and turns out they do. They make a whole and 4 more fifteenths. Could we do the same thing and subtract fractions? No? Can't subtract fractions? Well, why not? I can't just subtract fractions.
Yeah, you can.
You could? If I had 9 fifteenths of something, could I take away 10 fifteenths?
Yeah. No.
Well,
You could, but
well, how would that go? You have 9 fifteenths of a dollar, or no? And so I go to take 10 fifteenths from you. How do I take 10 fifteenths from you? I would take, well, all of your 9, and then what would we do? You owe me 1 more. So take the 9 you have, you owe me 1 more. How do we represent that in numbers? Negative. So who has negative 1/15 at this point? You. You have negative 1/15. You are negative 1/15. Okay. Yeah, it's a funny thing, negative numbers. But there you go. The thing is, to subtract fractions, we need still a common denominator, but the subtraction would work the same. Okay? So some common mistakes are adding straight across, adding and getting 5/8. We know we can't do that. We've displayed that. Also, doing kind of the same thing with people will go through the trouble of finding common denominator, then they'll add 9 and 10 and 15 and 15. Still add the denominators. Why don't we add the denominators?
Because they're the same.
Sure is the same. Sometimes things are the same when you do that. Yeah. Yeah, the denominator is representing what makes a whole. How many pieces make a whole? You want to, maintain that information throughout the whole problem. And say at the end, we have 19 of those 15th size pieces. All right. Are there any questions about adding or subtracting fractions? Sure. We could do 2/3 minus 3/4. Really similar problem. We need
12.
common
Denominator.
denominator. What will that denominator be?
12.
12. Multiply this by
4.
4 and this
By 4.
by 4. And use the same thing. This by 3. This by 3.
9 over 12 and 8 over 12.
8 over 12 minus 9 over 12 is negative 1/12. Just a note here, by the way. So we know multiply by 4 over 4. Now that's something we're actually doing. And here's why it's okay. What is 4 divided by 4?
1.
It's 1. And so what you're doing is multiplying by 1. And what happens when you multiply by 1? It's the same thing. Nothing happens. So we multiply by 1, but we just multiply by a convenient form of 1 so that the denominator becomes the same. So we'll just grab all of this. Well, most of it.
That's so cool. Oh, that's so cool.
That.
Oh, I made it smaller. Oh, yeah. I'm ready to do this one bit.
There's that operator.
Now we're going to deal with some multiplication and some division. Let's say 5 sevenths multiplied by 3/8. How do we multiply fractions together? How do we multiply fractions together?
Well, reciprocal. Yeah, I don't you do the roll, like, gonna flip it?
Flip it? No, we don't need to flip it.
That's for
You just go
division.
straight across.
Mhm.
So this will be 15 over what? 56. 15 over 56. There's the product of those two fractions.
That's it?
That's it. The only other thing we might do is simplify the fraction if that's possible. Let me show you an example of that. 5 sevenths times 9 tenths. Well, if I just multiply these straight across, I would get 45 over 70. And then I might notice, oh, these both have a 5 in common, and so I would simplify them to 9 over 14. All right, 12, 5, 12. Yeah, 9 over 14. But if we go all the way back here, we'll notice rather than mushing all of the factors together, right? 7 times 5 times 2, we put them together as 70, and 5 times 9, well, 5 times 3 times 3 into 45. They're smaller over here. All those factors are going to go together to make these two numbers anyway, so why don't we just look also across here and see if we can cross cancel. So this 10 could cancel this 5, that's a 1, that's a 2. And now when you multiply them together, we get the simplest fraction a little bit faster. It's a little easier to see that 5 and 10 share a factor of 5 and simplify it that way than seeing 45 and 70 share a factor of 5 and bringing it back down from there. So, yeah, that's multiplication. Let's say we want to take 5 sevenths and divide by 3/8. What's 5 sevenths divided by 3/8? Yeah.
Don't you have to like do the reciprocal thing here?
Yeah, you get a
Or-
reciprocal thing
So it'd be
here.
like 5 over 7 times 8 over 3.
Okay, are you sure it's not 7 over 5 times 3 over 8? You sure? And why? You're not?
Well, yeah, I'm sure. I think
What if I
so.
told you you were wrong and I told you that you had it backwards?
Then you told me I was wrong and I had it back?
Would you start doing it the other way? So you're not sure.
I guess not.
Well, do you want us to tell us you're wrong in all your college for math?
Yeah.
I mean,
What do you think?
never mind.
My point is, if you're sure and you know why you do that, or at least you can be sure that that's correct, then you can say, no, you don't do that. Let me show you. Let me show you why you can't do that.
I don't know why we do it, I was just taught that.
That's fine. It's good that you remembered it correctly, and you'll be fine if you keep doing that. So yes, the correct thing to do is 5 sevenths times 8 over 3. But just I like to have a little bit of a proof that that works, whatever it is, just so that I can, if I ever forget, remind myself. Okay? So we learned from finding common denominators that you can multiply, this fraction, any fraction, by the same thing in the numerator and the denominator. Okay? So if I multiply the denominator by 8/3, something nice happens there. What happens in the denominator? Yeah. Well, what is the denominator now? When I multiply these together, what do I have down here?
24.
Over 24 over 24. What's 24 divided by 24?
1.
1. So in the denominator here, I have a 1. Okay. I have a 1. What happens when you divide a number by 1?
It's the number over 1.
It's just, well, you can just write it as the number, right? You don't even have to write over 1. That's like, it's kind of redundant to write over 1. Divided by 1 doesn't change it. Well, I can't multiply by 8/3 in the denominator and not do it in the numerator, so I'll do that. And so now we get 5/7 times 8/3. 5/7 times 8/3. You could wind up with 7/5 times 3/8, but you would have to multiply the numerator by 7/5 and the denominator by 7/5, and you wind up 1 over that. So if you were given this problem, 5/7 divided by 3/8, and you did 7/5 times 3/8, what you have found in the end is actually the reciprocal of what you're supposed to find. So if you remembered correctly that 5/7 divided by 3/8 is 5/7 times the reciprocal, 8/3, great. If not, this is a nice little reminder. When you multiply the denominator and the numerator by the reciprocal of this fraction, the denominator kind of gets canceled out, and we get an easier problem. So here we have 40 over 21.
Alright, so all you gotta do is there's so reciprocate the one on the bottom.
The denominator.
And then just multiply.
And then multiply. So we divide fractions, multiply by the reciprocal of the denominator. Where was it for a second? I think we'll keep you on pace with fifth period. We got through here, and then we had a little discussion. So I'm going to play a video for you, and then see what you think about it. Oh, by the way, if you have any thoughts about class at any point in time, you can follow the directions on that white piece of paper back there on the orange board, and what it'll do is put it on this board. I tested it out. I put, any thoughts about class? It was great, right? That's what it'll look like to me, and it'll be fairly anonymous. I thought it was anonymous, then I found out I could reveal the last four numbers of a phone number. I don't know what good that would do me, but full disclosure, I could figure out the last four numbers of your phone number if you did that, but I have no interest in it. I just say that because I want you to know what you're doing and be informed about it. Let me get the speakers in. Watch this and just think about what it makes you think.
If you went to elementary school in the US, or much of the rest of the world, you almost certainly learned about something boringly called the order of operations, a set of rules for whether or not you should do multiplication before addition or addition before subtraction to get the right answer on your math test. Except you don't always get the right answer, or even one answer. I mean, is 8 minus 2 plus 1 equal to 5 or 7? And is 6 divided by 3 divided by 3 equal to 2/3 or 6? The problem is, focusing on the order of operations can lead to ambiguity and obscures the real, underlying, and often beautiful mathematics. A mathematician will tell you that 8 minus 2 plus 1 is really 8 plus negative 2 plus 1, which is unambiguously equal to 7, even though the so-called order of operations standard in the US tells you the answer is 5. If you want 5 for your answer, then you really need some parentheses. But why is this ambiguity even possible? It's because fundamentally, all of these operations are simply different procedures that start with 2 numbers and combine them in some way to give you 1 number. Each operation takes 2 numbers as input, 2 and no more. If you want to be entirely unambiguous and pedantic, every single pair of numbers in any algebraic expression should be inside parentheses. And then there's no need to know any order of operations. Just evaluate the innermost parentheses first and work outwards, collapsing them down pairwise like a championships bracket. But it turns out that's not the only way. It's possible to change the order in which you do the operations, to rearrange the parentheses, as long as you know what the underlying mathematics is. For example, if you want to add 3 plus 4 and then multiply the result by 5, you can either do the addition first and get 7 times 5 equals 35, or you can do the multiplication first, as long as you know that multiplication distributes across all the terms in the parentheses. That is, 5 times 3 plus 5 times 4 equals 15 plus 20 equals 35. The same answer. And how do we know multiplication distributes? One way is to draw rectangles, but I've done that before. The same rearranging can be done for exponentiation and multiplication. 3 times 2 all squared, or 6 squared equals 36, is the same as 3 squared times 2 squared, 36. It even works for addition and subtraction. 5 minus 1 plus 2 is 5 minus 1 minus 2. So the true order of operations is this. Use parentheses and learn what exponentiation, multiplication, addition, and the rest are really doing. Then you can proceed however you want. That's not to say that we don't have a conventional order of operations in mathematics. I mean, deciding that we evaluate multiplication before addition allows us to get rid of lots and lots of redundant parentheses. And noticing that 1 plus 2 plus 3 equals 1 plus 2 plus 3, and 2 times 3 times 4 equals 2 times 3 times 4 removes a ton more. But the point is that those parentheses are still there, still implied, just like how 3 minus 4 is secretly implying 3 plus negative 4, and 3 divided by 4 is really 3 times 1/4. But anytime the result might be ambiguous, you really need to use parentheses. Then you can proceed in whatever order you want. The order of operations learned in school, however, is different. It's a mechanical set of instructions that dictates just one of the many ways you can do algebra. It locks you into a single path through the beautiful mathematical landscape, which, while necessary for a computer whose goal is merely to give you the right answer, doesn't really give any insight onto what it is that you're doing when you do algebra. So while the order of operations isn't technically wrong, because most of the time it'll give you the standard answer, it's morally wrong, because it turns humans into robots. This minute...
Okay. Fast. Huh? It's fast? Is that what you said? It does write fast. Let's do this. I'm going to write a problem on the board and I want you to figure it out. Figure that out. common answers. 288 and 2. I first saw this problem on the channel of a YouTuber that I follow. And he just does math. He does actually pretty high level, like calculus and beyond, tutorials, physics, all sorts of different stuff. And so when this guy who I knew to be involved in tutoring higher level math and physics put this problem on a video and then asked for help, I thought that was really silly. It's really easy. So I did it, and I got, what my conclusion would be, and then read the comments and discovered just a huge controversy over this problem. Just like 500 comments in just a few hours, with people really vehement, cursing at each other, getting really mad over this. Okay? When I said 2, if you got 288, none of you just flipped out, and vice versa. Nobody freaked out when I put these other numbers up here. If I say, I got 288, and you're one of the people who got 2, we might be able to get into a heated debate about it, maybe. Let's look at how we can get to these 2 answers. I think almost everybody, except for actually at least one person, and this is rare, most people added these 9 and 3 together. Okay? Most people will do that. 48 divided by 2 times 12. Add 9 and 3 and you get 12. Okay? Where you proceed from here is usually where you diverge from one person to the other. Either you divide by 2 first, or you multiply 2 by 12 first. One of those things has to happen. So this is 24 times 12 if you divide first, or it's 48 divided by 24 if you multiply those together first. And so 24 times 12 is 288, and 48 divided by 24 is 2. So the question is, like, in that debate, in those 500 comments to that video, who was right? These people or these people?
288.
288 people were right?
No.
The 2 people were right. Okay. What do you think?
I think the left.
Who feels strongly that 288, the people who said 288 are right, and that, keep your hands up if you think that you're right and the people who got 2 are wrong. Oh, now you're not so. Okay. You think that your answer is correct, but if you put your hands down, you think, well, I'm not going to tell people who got 2 that they're wrong. Now, who thinks that 2 is right? You got 2 and it's right, and the people who got 288 are wrong.
I redid it.
Well,
I
288
saw what I
just
did
has
wrong.
like an extra step to it. 'Cause then
288 had an extra step?
Yeah, because you times those 2 and then you
Well,
Well, you could do it another
we just
way.
divide 48 divided by 2 is 24, and then that 24 times this 12 gave
Billy's
288.
one of those persons that's going to have a heated conversation.
No, I'm not. I just know. No, you
Well, I'm
can't.
calling
No
out
way.
Caitlin.
If this was on a homework assignment,
Yeah.
which one would you say wrong?
We'll talk about that. What my conclusion would be if it was on a homework assignment. Hunter.
Don't you have to go left or right?
Yeah.
Okay, so there's in lies the strongest argument is you have to go left to right. Or what's the other argument?
Well, no,
No, I want the other argument. I don't want Hildy's
Oh,
whatever she's thinking. Yes?
Like the PEMDAS, you're supposed to multiply the 40.
Okay, so when we write this down, here is what it all came down to. All the arguments came down to, well, to this or one other thing. This is what I learned. I learned that you do PEMDAS, and if you read it, you idiot, right? Somebody might call someone else an idiot on there. If you read it, look, M's first in your face.
You can do either one first.
Yeah.
And you can do this adding and subtraction first.
Here's the thing. Here's the thing. In his video, he brought up, well, here's an even better one. The one that he brought up, 6 divided by 3 divided by 3. He did it 2 different ways. And one way, he did 6 divided by 3, which is 2 divided by 3, and he got 2/3. Or he did 3 divided by 3, he got 6 divided by 1, and got 6. And here's the thing, this could be representing 6 divided by 3/3, or 6/3 divided by 3. Right? It could be either one of those.
Just like how he set it up, how he set up the problem.
What about how he set up the problem?
Just anybody could think about it a different way.
Exactly. Anybody could think about it a different way. And is one way wronger than the other way? Is one way more right than the other way? Here's what happened. Here's what happened. I like to tell little stories to myself about the history of mathematics. Okay? So at some point in history, we decided there were numbers. Okay, we understood that. And then we decided that there were these operations, like multiplication, division, and the subtraction, and all those guys. And we decided that's how these numbers will interact. Okay? That's all that's really been decided, and everything else is built off of that. So what about the operations, division, and multiplication make it so that this should come first before this, or that this should come first before that? What about the actual operations and numbers being in existence tell you that you're supposed to do those things first? Nothing. This tells you you're supposed to do those things first. A thing that a teacher told you. Okay. Now, that teacher, whoever they were, was part of a math community. And the math community is made up of a lot of people who like to use as little ink as possible. Okay? If we were to do math as he suggested and be completely clear about everything and have there be no confusion, we'd have to use a lot of parentheses, right? Yeah. But we decided, as mathematicians who don't like to use lots and lots of ink if we can avoid it, instead of writing lots of parentheses, this is, I imagine all the mathematicians of the day got together long, long ago in history and decided, let's do this like a PEMDAS thing. Let's just decide that certain things will come first. Okay? Parentheses. Let's do stuff inside the parentheses if possible first. Then we'll do exponents. Let me show you an example where you just need to agree to do exponents first. It's an agreement. It's not absolutely dictated by the notation. It's just an agreement. If I do 2 times 3 squared, what should that come out to be?
18.
It should come out to be 18 according to the agreement that we've made. The agreement about the order that we'll do things. The agreement says, I will take this and imply that it only applies to this 3. Now there's nothing about squaring something, about taking something to the second power, that requires it to only be applied to this number. But that's the agreement we've made. Exponents first. They're very high on the list. They're second. So they come very close to the top, very close to the first thing you do. Then you take your 9 and multiply it by 2. But that's only because of this. You could, if you didn't know anything about this PEMDAS thing, you could just multiply 2 times 3, get 6, square it, get 36. I see numbers, I just don't know which is supposed to be first, other than we agreed to make some of them first.
I did mine again because I didn't know which one was right. So when I did it the second time to get 2, I did it different though. And I just want to know if it was a fluke accident that it turned out right, or it's supposed to. Because I didn't get to do it the same way you did.
To get 2, but you got 2?
Yeah, I got 2.
Then you probably did something really similar. Did you like distribute the 2?
Yeah.
So there's another question. Even if you distribute the 2, I'm only going with the most popular answer. What if I distribute the 2 and get 48 divided by 18 plus 6? Right? Or sorry, 18 plus
that makes
6.
sense, sorry.
18 plus 6. Well, now do I divide this by 18? Or do I add 6 to 18 and divide by the result?
Well, I still had the 18 and the 6 in parentheses.
That was your choice, wasn't it? You decided to put parentheses, right? That's what I'm saying. Like, all these things are choices. Okay?
This is confusing, I hate math.
There is going to be a way that we subscribe to in this class. It'll be the way that I was taught. It'll be the way probably my math teachers were taught for generations before. It's the way this book talks about it. It's the way our calculators, these calculators, will do it. If I put this in my calculator, 48 divided by 2, parentheses, 9 plus 3. Okay, just like that. I don't have that same symbol, but that means division right there. It gets 288. Is that because the calculator's right and anybody who gets 2 is wrong? No. You'll find I like calculators, I like technology a lot, but when it becomes a crutch, that's when I start to hate it. Okay? So as soon as you start to pass the line from helpful to crutch, I'll lean into you and help you get away from this if possible. Okay? So I'm going to put that away though. The problem really is that it's a poorly constructed phrase. It's like a mathematical phrase. It's an expression. It's a poorly worded expression that is confusing. Have you ever read a sentence that you're not sure what it meant? You can interpret it 2 different ways. I should really look these up. There's like these good examples of putting the comma in a different place completely changes. Huh? Oh, let's eat grandma. It could be let's eat grandma, or let's eat grandma. Right? If you don't use punctuation very well, that could sound really sick.
Grandma's my favorite figure.
Let's see, Grandma.
Hold on. The first part of leaving class is waiting, right? Remember, waiting, not packing up your stuff until I ask you to. And we have plenty of time to finish up what I'm trying to say, okay? We will do it the way that the calculator just did it, and that is more written this way. I think I saw this in Mr. Zalay's classroom. P-E-M-E-A-S. So what's the implication here? Either or, multiplication or division, which takes priority? They do, just whatever's on the left is first, and then you go from left to right. Not because it's right, but it's because we agreed to do. This is what we'll agree to do, okay? And then to answer the question of is this was on the homework or if this is on a test, the answer would be, that's my fault. I was not clear in what I was saying, okay? If you want to get the expected answer, the answer that I would expect to get would be 288, but I also realize this is really ambiguous. If I want you to get 288, what I'll write is 48 over 2 times 9 plus 3. No way you can get 2 that way. You have to divide these 2. That's what I want you to do. And when you get done, you'll have to multiply that by the result of 9 plus 3. Even if you distribute it through the parentheses, you'll still get 280. Okay? No way you can get a different answer. And so if you were to get 288, I would say, oh, right, that's exactly what I thought. And if you got 2, and another person got 2, and several people got 2, I would look at that question and say, that was a poorly worded question. And either I'll give you credit for it or I'll take it off the test. Okay? I try to be fair. I try to be clear. All right. So any other thoughts? All the arguments, all hundreds of comments came down to, this is the way I was taught, or this is what calculator said. Calculator, or Google, or computer algebra system, or whatever it is they were using, they just trusted it implicitly. And you can actually buy calculators that do it this way and get 2. There are calculators out there. They're not as common. Probably because just Texas Instruments was really good about getting their calculators into the schools, getting schools to buy into them, and that's why there's so many of them all over. But yeah. Yeah. So yeah, you can put your stuff away, and we'll be leaving in about 45 seconds. You can write down the homework, or the homework is on the website, or the homework is coming out on text messages.
Oh, so all the problems will be on the test then?
Yep.
Okie dokie, that's a lot.
And all those questions.
It's just these two. 2.1 and 2.2.
Yeah, the left to right thing.
Yeah, the right side, right, and then you multiply that other right side. Well, the thing is not about if it's right or wrong, it's about making an agreement. We agree to do it that way. It's like, is it right to drive on the right side of the road or the left side of the road?
It's right to walk away.
You're supposed to walk against traffic.
Oh, so now wait. Alright. So we're supposed to walk with.
Then right against traffic and walk against traffic.
So bikes with. Oh, okay.
I know, no, I'm sugar.
Let's get in our seats. That's where we should be. This is not a stand up until the bell rings kind of class.
Is that did you play?
Is it what?
Or did you say?
Yeah, 2.1 and 2.2.